Hello everyone, welcome to our channel Lessons of Life. In this video, we are going to discuss few problems based on bitwise operations. These problems have been handpicked from the Codeforces problem set and are varying difficulty level. Each problem is based on a different concept, so I hope you will get to learn something new from each and every problem.
चल झूठा
Although I will be reading the problem statement aloud while discussing the problems, it would be better if you yourself read the problem statement by pausing the video when the problem is displayed on the screen. Also, before directly seeing the solution, you should pause the video and try to figure out the hidden logic yourself, because that will leave a greater impression on you as compared to directly seeing the solution. So if you are new to the channel, please subscribe to the channel, and if you find the video worth watching, then please recommend and share it with your other friends also. So without wasting any time, let us start discussing the problems.
तो करना परेशान हो गए हम लोग 2.5 साल से.
Okay, so these are the 6 problems that we are going to discuss. So let us begin with the first problem. Okay, so the problem is and 0 sum big. Baby Badavi's first words were and 0 sum big. So he decided to solve the following problem. Given two integers n and k, count the number of arrays of length n such that all its elements are integers between 0 and 2 raised to the power k minus 1 inclusive. The bitwise end of all its elements is 0. The sum of its elements is as large as possible. Since the answer can be very large, print its remainder when divided by 10 raised to the power 9 plus 7. Okay, so we have two integers n and k. For each step, print the number of arrays satisfying the conditions. Okay, so the question gives us two integers n and k. We need to construct an array of n integers, and we have 3 requirements. First, all its elements are integers between 0 and 2 raised to the power k minus 1. So what does this mean? It means that the maximum number of bits that we can have in any element of our array is k, because the element should be between 0 and 2 raised to the power k minus 1. The second requirement is that the bitwise end of all the elements of our array should be 0. And third is the sum of its elements is as large as possible. So we need to count the number of arrays which satisfy all these 3 requirements. So let us consider how can we construct this array. So suppose a1, a2 all the way up to an, these are the elements of our array, and 1, 0, these are the binary representations of our elements of the array, which are made up of k bits, is specified by the first requirement of the problem. Now we want the bitwise end of the elements of the array to be 0. The first important thing to note here is that all the bits are independent of each other. So if we want the first bit to be set to be 0 in the result, that is the bitwise end, so we need at least 1 0 in the first bit of all the numbers, because if all these bits are set to 1, then we cannot have a 0 in the bitwise end of all the results. Similarly, if we consider the second bit, if we want 0 in the bitwise end, then we need at least 1 0 in the all the second bits of all the elements of the array. Similar is the case for all the other bits of our elements of the array. For each bit place, we need at least 1 0. Then only our bitwise end can be 0. But the third requirement says that the sum of all the elements of our array should be as large as possible. So the sum will be very large when all the other bits except that 1 0 that we will require for the bitwise end to be 0, all the other bits are set to 1. For example, if we consider the first bit place, then in the first bit place we need only 1 0 for the bitwise end to be 0, and all the remaining other bits should be set to 1. Then our sum will be maximum. Similar is the case for the second bit, and all the remaining bits, that only one bit should be set to 0 and all the other bits should be set to 1. But the question is, if we consider the first bit, where can we place the 0th bit? So we can place the 0th bit for the first element, for the second element, all the way up to the nth element. So we have total of n choices to place the 0th in the first bit place. Similar, for the second bit, we have a total of n choices for the first element, second element, all the way up to the nth element to place the 0. So we have a total of k bits, and for the all the k bits, we have a total of n choices. So our answer will be n to the power of k, because for each bit we have total of k choices. So the number of ways in which we can construct our array is n to the power of k. So let us try to code out the solution. So we will use the online compiler. So first ln n, k, and cout answer. So let us check we are getting the correct output or not. 4 and 2 to 6, 732. Okay, so let us submit it. So the language is not correct. Yes. Now let us submit it. So yes, it got accepted. So we did the first problem.
मजा आया और मैं ये जो मजा है हिंदुस्तान के हर व्यक्ति को देना चाहता हूं.
Okay, so now let us move to the second problem. Okay, so our problem is XOR wise. In order to celebrate twice 5th anniversary, Zuyu and Sana decided to play a game. Zuyu gave Sana two integers A and B and a really important quest. In order to complete the quest, Sana has to output the smallest possible value of A XOR X plus B XOR X for any given X, where this operation denotes the bitwise XOR operation. Input: each test contains multiple test cases. The first line contains number of test cases T. Description of the test cases follows. The only line of each test case contains two integers A and B. One is less than or equal to A comma B less than or equal to 10 raised to the power 9. For each test case, output the smallest possible value of the given operation. Okay. So in the question, we will be given two integers A and B, and we need to output the minimum possible value of A XOR X plus B XOR X, and we can have any choice of X according to our wish. So let us discuss the approach to this problem. Okay, so our answer consists of two parts. The first part is A XOR X and the second part is B XOR X. Suppose if we consider the first bits of the two integers A and B that we are given in the input, if the first bits are different or any particular bits of both A and B are different, for example, if you consider here the first bits, the first bit of A is 0 and the first bit of B is 1. So they are different. So what choice can we have for X? If we choose the first bit in X to be 0, then 0 XOR 0 for A part will be 0. So this part will remain 0. But for the B part, 0 XOR 1 will give us 1. So this part will become 1. In contrary, if we choose that bit of x to be 1, then 1 XOR 0 will be 1. That means this part will give us 1, and B 1 XOR 1 will be 0. So this part will remain 0. So if the particular two bits of A and B are different, then for that bit of x we can have any choice. Either it can be 0 or it can be 1. Because for both 0 and 1, either A XOR x will increase or B XOR x will increase. So we can have two choices. But if the two particular bits in A and B are both 0, suppose the second bits, they are both 0. So if we choose that particular bit in our x to be 0, then our answer will be 0 XOR 0. So it will remain 0, and 0 XOR 0. So it will also remain 0. So it is beneficial for us to maintain a minimum answer. In contrary to this, if we choose that second bit in x to be 1, then our answer will be 0 XOR 1 will be 1. So this will increase, and 0 XOR 1. So this will also increase, which is not beneficial for us because we want to minimize this value. So if both the bits of a particular position in A and B are both 0, then that particular bit in our x should also be 0 in order to obtain a minimum answer. Now, if the bits of A and B at a particular position are both 1, is the third bits in A and B in this example, if they are both 1, then that particular bit in our x should also be 1, because then 1 XOR 1 will be 0, so this will be 0, and 1 XOR 1, this will also be 0. So if both the bits at a particular position in our x, in our A and B are 1, so that particular bit in our x should also be 1. So what conclusion can we derive from these operations? If the bits at a particular position in A and B are different, either they are 0 and 1, or they are 1 and 0. For that case, we can have any choice. Either the bit in x can be 0 also, or that bit in x can be 1 also. Let us say we will choose 0. So if the bits are different, 0 and 1 or 1 and 0, then we will have that particular bit in x to be set 0. But if the bits at a particular position in both x and b, in A and B, are both 0, then that particular bit in our x should also be 0 in order to obtain a minimum value of A XOR x plus B XOR x. And if that particular bit in A and B is both equal to 1, then that bit in x should also be 1. So what does this table look like? 0, 1 should give us 0, 1, 0 should give us 0, 0, 0 should give us 0, and 1, 1 should give us 1. So it is nothing but an bitwise AND operation. So we should first find the value of x by applying a bitwise AND operation on A and B. And then using that value of x in this expression, we can calculate the minimum possible value of A XOR x plus B XOR x. So now let us move to the code. Okay, so let us code it out. LLT C in T while T minus minus A B A B LLX is equal to A and B. Then our answer will be A XOR x plus B XOR x. So let us check if it is working for the test cases. 10, 13, 8, 91, 18. 10, 13, 8, 9, 18. Okay, so if it is working, let us try submitting it. Okay, so it got accepted. I hope you understood the second problem also.
यही नहीं, अभी और सुनिए।
Okay, so now let us move to the third problem. So the problem is, and then there were k. Given an integer n, find the maximum value of integer k such that the following condition holds: n and n minus 1 and n minus 2 and n minus 3 all the way up to k is equal to 0, where ampersand denotes the bitwise AND operation. So the first line contains a single integer t. The test case is, the first line of each test case contains a single integer n. So we will be given an integer n as an input, and we need to print the maximum value of the integer k such that n and n minus 1 and n minus 2 all the way up to the k is equal to 0. So let us understand this problem by taking an example. Suppose n is equal to 6. So the bitwise representation of 6 is 110, for 5 101, for 4 100, and so on. If we consider the numbers up till 4, then the bitwise end of all the bits except the most significant bit is 0. For example, if you consider the last bit, then the bitwise end of 0 1 0 is 0, 1 0 0 is 0, because in 4 we have all the bits set to 0 except the most significant bit. So all the way up till 4 we have the bitwise end of all the bits to be 0 except the most significant bit. So if we select our integer k to be 4, then all our bits will be 0, but the most significant bit will not be 0, but we want it also to be 0. So we need to select one integer less than 4. If we select k equal to 3, and then the bitwise end of all these numbers from 6 to 3 will be 0. 0 and 1 and 0 and 1 will be 0. Similarly, for this bit we have at least one 0, so the bitwise end will be 0, and for the most significant bit also the bitwise end will be 0. So we went up till 3. So what is 3 here? 3 is 1 less than the maximum power of 2, which is less than 6, because our the given n in the question is 6. So the maximum power of 2, which is just less than 6, is 4. So we need to go all the way up to the 1 less than the maximum power of 2, which is less than 6, that is 3. If we take another example, suppose, now let us consider that n is equal to 17. Then the bitwise representation for 17 is 1 0 0 0 1. For 16 it is 1 0 0 0 0, and for 15 it is 1 1 1 1. If we consider up to 16, then for all the first 4 bits the bitwise end will be 0, but the bitwise end will not be 1, will not be 0 for the most significant bit. So in order to make the bitwise end of the most significant bit also to be 0, we need to consider the integer 1 less than the maximum power of 2, which is less than 17. In this case, our n is equal to 17. So we need to find out the maximum power of 2, which is just less than 17. So it is equal to 16. Now our required answer will be 1 less than 16, which is 15. So what is our conclusion? The required value of k is 1 less than the maximum power of 2 less than n. So let us see the code for this problem. Okay, so now let us code the solution. First we need to take the input for n. Then let us take a variable temp. We need to find out the maximum power of 2, which is less than given n. So we can do it. L temp is equal to root of log 2 base 2 of n then answer is equal to 1 left shift temp minus 1. Actually, there is no need for this parenthesis. So let us check for the test cases 1, 3, and 15. So yes, let us try submitting it. So yes, it got accepted. I hope you understood the third problem also. Okay, so now let us discuss the fourth problem. Okay, so the problem is Mocha and math. Mocha is a young girl from high school. She has learned so much interesting knowledge from her teachers, especially her math teacher. Recently, Mocha is learning about binary system and very interested in bitwise operation. This day, Mocha got a sequence A of length n. In each operation, she can select an arbitrary interval L to R, and for all values I, 0, less than or equal to R minus L, replace A L plus I with A L plus I plus 1 and A R minus I at the same time. If you do not understand the operation, do not worry, I will explain it. Where ampersand denotes bitwise n operation. This operation can be performed any number of times. For example, if n is equal to 5, the array is A1, A2, A3, and 5, and Mocha select the interval 2 to 5. So if she selects in the interval 2 to 5, then the new array is A1. A1 will remain itself because it is out of the interval. A2 and A5. A2 and A5. A3 and A4. A3 and A4. Then A4 and A3. A5 and A2. Okay. So this is how we can change the array. Now Mocha wants to minimize the maximum value in the sequence. As her best friend, can you help her to get the answer? So we want to minimize the maximum value present in the sequence. Okay. The first line of each test case contains a single integer n, the length of the sequence. The second line of each test case contains n integers. For each test case, print one integer, the minimal value of the maximum value in the sequence. Okay, so let us first understand how this operation is performed on the array. Suppose our initial array is A1, A2, A3, A4, all the way up to AN minus 2, AN minus 1, and AN. What Mocha can do is that she can select the elements which are symmetrically placed from the beginning and from the end and replace them with their ends. For example, if in this particular case our L is equal to 1 and R is equal to N, then what she can do is replace A1 with A1 and AN. So A1 will be replaced with A1 and AN. Then A2 will be replaced with A2 and AN minus 1. So A2 will be replaced with A2 and A minus 1. Similarly, A3 will be replaced with A3 and AN minus 2. So A3 will be replaced with A3 and A minus. Similarly, for the last elements also, AN minus 2 will be replaced with AN minus 2 and A3. AN minus 1 will be replaced with AN minus 1 and A2. And the last element AN will be replaced with AN and A1. So this is the way in which Mocha can apply the operation on the array and change the array. So now, what are the key points about this operation? The first point is we can neither perform addition nor subtraction on the values of the elements of the array. The only operation we have is the bitwise AND of the elements of the array. So this is true. We can neither add nor subtract. With the only operation we can perform is the addition of the element, not the addition, only the bitwise AND of the elements of the array. So what is the minimum possible value we can achieve? So definitely if we are allowed only to do the bitwise AND, and the bitwise AND is smaller if we include more and more elements, so it is the bitwise AND of all the elements of the array. If we are including all the elements of the array, then that is the minimum possible value that we can achieve, and we want only, we want the minimal value of the maximum value present in the array. So in order to minimize the maximum value which is present in the array, we can obtain, what we can get is the bitwise AND of all the elements of the array. But how can we achieve it? That means, in what order can we apply the operation to the array so that every value in the array becomes equal to the bitwise AND of all the elements of the array. So let us see the order in which we will apply the operation so that every value in the array becomes equal to the bitwise AND of all the elements of the array. So this is our initial array A1, A2, A3 all the way up to AN. So first we can select L equal to 1 and R equal to N. So our array will be transformed to A1 and AN, A2 and AN minus 1, A3 and AN minus 2. Similarly, the last element will also be transformed A3 and N minus 2, A2 and AN minus 1, A1 and AN. So this was the first step of the operation in which we selected L equal to 1 and R equal to N. Now what we can do is we can select L equal to 1 and R equal to 2. So the new array will be A1 and AN and A2 and AN minus 1, because this was our first element and this is our second element, and this will also get transformed to A1 and AN and A2 and AN minus 1. All the other remaining elements will remain as such. Now in the further steps, what we can do is we can select L equal to 1 and R equal to the third element. So now A3 and AN minus 2 will also get included in this bitwise AND. In the next step, we can select L equal to 1 and R equal to 4. In this way, we can include all the elements from 1 all the way up till n in the bitwise AND, so that the minimal value what we can get is bitwise AND of all the elements present in the array, and that will be our answer. So let us see the code for this particular problem. Okay, first ln in n a of n or if I is less than I plus in a of I. Now ln answer is equal to 1. We need to find bitwise AND of all the elements of the array. So let us see if it works or not. 0 1 3 3, this is what is desired. Okay, so there is some error. Let us check. Okay, so our answer should be AO 0 initially. Now it is correct. Let us try submitting it. So yes, it also got accepted. Okay, so now let us move to the fifth problem. So the problem is rock and liver. Danik urgently needs rock and liver. Obviously, the easiest way to get these things is to ask Hermit Lizard for Adim. Hermit Lizard agreed to give Danik the liver. But to get a stone, Danik needs to solve the following task. You are given a positive integer n and an array A of positive integers. The task is to calculate the number of such pairs ij such that I is less than j and ai and aj is greater than or equal to ai XOR aj, where ampersand denotes the bitwise AND operation and this operation denotes the bitwise XOR operation. Danik has solved this task, but can you solve it? So we need to count the number of pairs I, j such that I is less than j and the bitwise AND of the ith element and ajth element is greater than their XOR. Input. The first n contains one positive integer t denoting the number of test cases. The first line of each test case contains one positive integer n, length of the array. The second line n contains n positive integers ai, the elements of the array. Okay. For every test case, print one non-negative integer, the answer to the problem. That is the number of pairs ij such that ai and aj is greater than or equal to ai XOR aj. So let us discuss the approach to this problem. So the first point to note is that the constraints are so large that we cannot iterate over all the pairs of I and j because it will require an order of O of n square. And in the problem, our n is of the order of 10 raised to power 5. So if we apply an approach of O of n square, we will get a TLE. So what else can we do? In all such problems where we want to count the number of pairs I and j satisfying a certain condition is in the current problem, then always remember that we need to store the frequencies of a particular property of all the elements of the array. But what is that property in this case? So let us understand this with an example. Suppose our any ai element is 1 0 0 1 1 0 and a jth element is 0 1 1 0 0 0. If we find out the bitwise AND of these two elements ai and aj, then the bitwise AND of this element is 0 0 1 0 0 0. And similarly, if we try to find out the bitwise XOR of these elements ai and aj, then the bitwise XOR is 1 1 0 1 1 0. So if we see the bitwise XOR of these elements ai and aj is greater than as compared to the bitwise AND. So this pair of I and j does not satisfy our requirement because we want that the bitwise AND should be greater than the bitwise XOR. Now let us consider another example of ai and aj. Suppose ai is equal to 0 0 1 0 0 1 1 0 and aj is 0 0 1 0 1 0 0 0. Again, if you try to find out the bitwise AND and bitwise XOR of these two operations of these two elements, then the bitwise AND is 0 0 1 0 0 0 0 and 0. Similarly, for these two elements, the bitwise XOR will be 0 0 0 0 1 1 1 0. Now, in this case, the bitwise AND of these two elements ai and aj is greater than their bitwise XOR. So now these two elements satisfy our requirement that the bitwise AND is greater than or equal to the bitwise XOR. But why it is like that? For these two elements, the bitwise AND is smaller than the bitwise XOR, but for these two elements, the bitwise AND is larger than the bitwise XOR. The reason is that the number of leading zeros in both ai and aj is the same. In aj, the number of leading zeros is 2. Similarly, in ai also the number of leading zeros is also 2. So if any two given elements, the number of leading zeros is same, then the bitwise AND will always be greater than the bitwise XOR. But in contrary to this, if we consider this example, then in ai the number of leading zeros is 0, but in aj the number of leading zeros is 1. So the number of leading zeros in ai and aj is different in this case. Therefore, the bitwise XOR is greater than the bitwise AND. So if we want the bitwise AND to be greater than the bitwise XOR, then the number of leading zeros in both the elements should be the same. So our third point is for any two given elements ai and aj, the bitwise AND will be greater than bitwise XOR if the number of leading zeros in both is the same. So how can we count the number of leading zeros? For counting the number of leading zeros, we can use the function underscore underscore built in underscore CLZ that return the number of leading zeros. Okay, so what will be our approach? We will create a map to store the frequency of leading zeros. Then For each element ai as we iterate, we will check how many earlier elements have the same number of leading zeros, and they will form a pair of I and j. So let us see the code. Okay. So first we need to take the input n, ln n, c in n, then vector a of size n, then we need to create a map mp. Answer will be initially to 0. Then we need to iterate over all elements. Answer plus equal to mp of underscore underscore built-in underscore clz ll, because we are using the data type long of a of I. So answer plus is equal to mp of underscore underscore built-in clz ll of a of I, and after that we will increase the value. And we will finally print the answer. So let us check the test cases. 13200. So 132, let's try submitting it. Okay, so yes, it got accepted. This was our fifth problem. So now let us discuss our last remaining problem. So our problem is min max cut. A binary string is a string that consists of characters 0 and 1. Let MEX of a binary string be the smallest digit among 0, 1 or 2 that does not occur in the string. So I hope all of you know about the MEX. MEX is the minimum element which is not present in our array or the string. For example, MEX of 001 is 2, because the minimum element which is not present in this whole string is 2, because 0 is present, 1 is present, but 2 is not present, because 0 and 1 occur in the string at least once. MEX of 1111 is 0, because 0 and 2 do not occur in the string and 0 is less than 2. A binary string S is given. You should cut it into any number of substrings such that each character is in exactly one substring. It is possible to cut the string into a single substring, the whole substring. A string A is a substring of a string B if A can be obtained from B by deletion of several characters from the beginning and several from the end. What is the minimal sum of MEX of all substrings pieces can be? So what we need to do is we will be given a binary string and we need to divide the string S into any number of substrings such that the sum of the MEXs of all the substrings is as minimum as possible. The input, the first line will give us the number of test cases. Each test case contains a single binary string S whose length can be at most 10 raised to the power 5. Output, for each test case output a single line, the minimal sum of MEX of all substrings that is possible to get by cutting S optimally. So we need to cut S into substring such that the sum of the MEXs of all the substrings is as minimal as possible. So let us see what are the different cases possible for this problem. So case first, suppose if the string consists of only zeros. If the string consists of only zeros, then we can take the string as a whole, and then the MEX of the string will be 1. For example, let us say S is equal to 0, 0, 0, 0. In this string, the string consists of only 0. So if we take the whole string, then the MEX will be 1. Similarly, if S is equal to 0, 0, 0, 0 and any number of zeros such that no 1 is present, then we can take the whole string as one substring, and then the MEX of the string will be 1. Case second, if the string consists of only ones. Suppose if there is no 0 present in the string, then we can take the string as a whole again, and then the MEX of the string will be 0 because now 0 is not present and 0 is the minimal character. For example, if S is equal to 1, 1, 1, 1, then we can take this string as a whole, one substring, and then the MEX will be 0 because 0 is not present in the string. Or S is any number of ones as large as possible, but all ones, no 0, then again we can take the whole string as one substring, and then the MEX will be 0. But now let us consider the case third, if the string consists of both zeros and ones. So in this case, there are two subcases possible. If the zeros are consecutive, then the MEX will be 1. How? Let us see. For example, if S is equal to 0, 0, 0, 0, 1, 1, 1, 1. In this case, both zeros and ones are present in our string, but all the zeros are present together. That means they are present consecutively. So we can select all the zeros from 0, 0, 0, 0 is one substring, and 1, 1, 1, 1 is another substring. For the substring with all the zeros, the MEX will be 1. And for the remaining part where all ones are present, the MEX will be 0. So the sum will be 1 plus 0 will be 1. Similarly, if you see for string S equal to 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 1, here also all the zeros are present together. So if we take all the zeros as one substring, the starting part is 1 and the last part is another substring, then for this substring with ones, the MEX will be 0. For this part also the MEX will be 0, and the part with the consecutive 0, the MEX will be 1. So the sum will be 0 plus 1 plus 0 will be again 1. So if the zeros are present consecutively, that means if they are together, then the MEX of the string will be 1. But the second subcase, if the zeros are not consecutive, then the MEX will be 2. Because, for example, S is equal to 0, 1, 0, 0, 1, 1, 1, 1. Now, in this case, zeros are not present consecutively because we have 1, 1 between zeros. So, if we select this whole string as one substring, then the MEX for this substring will be 2. Because 0 is present in this substring, 1 is present, and 2 is a minimal character which is not present. So, the MEX will be 2. Similarly, if we take this substring, then in this string also the zeros are not present consecutively. We have two ones in between the zeros. So in this case also, if you select the zeros as one substring, then the MEX will be 2 because 0 is present, 1 is present, and 2 is the only character which is not present. So the MEX will be 2. So there were three cases possible. First, if the string consists of only zeros, then the MEX will be 1. If the string consists of only ones, then the MEX will be 0. And in the third case, when the string consists of both zeros and ones, then there are two subcases possible. If the zeros are consecutive, that means if they are present together, then the MEX will be 1. Otherwise, if the zeros are scattered, that means they are not present consecutively or together, then the MEX will be 2. So let us now apply this in code and let us see how can we get the solution. Okay, so string s in s, so let us store the length in n, then we can count the number of zeros. If s of I is equal to 0, then zeros plus plus. If the number of zeros is equal to n, that means if all the zeros are present, then we need to say out 1. else if zeros is equal to, that means all ones are present, then we need to see out 0, else we need to check whether all the zeros are present consecutively or not. For that, we can check by else dot find 0 and ll last is equal to s dot r find 0. So first we'll store the first occurrence of 0 and last will store the last occurrence of 0. Now in order to check if the zeros are present consecutively, if last minus first plus 1 is equal to the number of zeros, that means the zeros are present consecutively, then we need to see out 1, else we need to see out 2. So this was our solution. Let us see if it works for the test cases. So we should get 102 and 112. So 102 and 112. Let us see. Let us try submitting it. If it gets accepted or not. Let us see. Okay. So yes, it also got accepted. So this was our last problem. Okay. So these were the 6 problems that we discussed in the video. I hope you liked the video and found the video useful.
नहीं.
So please subscribe to the channel and also share it with your friends who might have not subscribed the channel till now.
चलिए मान लीजिए कि मैं बुरा आदमी हूं, पर आप तो अच्छे हो ना, तो थोड़े अच्छे बनो.